Okay, good morning, everyone. Hope you had a good weekend. Today we are reviewing linear stability analysis. So a couple of lectures ago, just before the midterm, I asked who remembered linear stability analysis, and quite a few people put up their hands saying that they wanted to have a reminder. So we're going to go through that today. And the reason we're doing this is because we've recently met this method, adaptive dynamics, for modeling the long-term phenotypic evolutionary dynamics of a population. And one of the key assumptions of adaptive dynamics is that there is this separation of timescales. So we're separating out our ecological or population dynamics timescale, so changes in population size, say, from our evolutionary timescale, where we're having changes in our phenotypes or our traits. Okay, so what this comes about because we're assuming that mutations are very rare. We do this because it means that we can simplify the analysis, essentially. So if you recall, when we're looking at our invasion fitness, we only care about the dynamics of our mutant because we're assuming that our resident population is at some steady state. We don't actually have to assume that it is at steady state. We can have limit cycles and stuff like that, but we're not going to cover that in this course. There are methods to deal with that, but they're a bit more complicated. Here, we're just going to assume, that we've always reached this steady state, or at least we should check that it reaches a steady state first. So yeah, the first step to adaptive dynamics is considering those ecological dynamics, those population dynamics, and checking that there is some equilibrium which the system will tend to. In other words, that equilibrium is locally asymptotically stable. Okay, so we tend to that stable state. Then we can allow a mutation to happen and see how that rare mutant fares, whether it is able to spread or not, depending on its invasion fitness. Okay, so in order to do adaptive dynamics, we therefore need to know linear stability analysis. So we're going to recap this stuff. Hopefully, you should have met this stuff before. If not, it should contain everything you need to know. Okay, we'll go through an example at the end as well. So we'll recap equilibria or steady states, linear stability analysis, what it means, what we're actually trying to do. We'll meet the Jacobian again. We'll talk about perturbations and ideas about local stability rather than global stability. This idea of asymptotic stability, which basically means we're just tending towards an equilibrium in the long term, and something called the Routh-Hurwitz conditions, which can help you simplify some of the analysis. Okay, so let's start off considering a nonlinear system of autonomous ordinary differential equations. Okay, so that will look something like this. In vector notation, dx dt is equal to some function f of x of t. I'm going to put my t here just for now, just to make sure it's clear. So x of t is just some n-dimensional state vector. So by state vector, you can think of this as being your different population sizes. So this could be, hosts that are not infected, but are infected after 1 day, 2 days, how many days. It could be number of prey, number of predators. It could be number of juveniles, number of adults, number of males, females, and so on. Some kind of state vector describing the state of your population at time t. And this is in Rn. And then this function here, this is f. Again, it's just some function that maps the current population at time t to the population instantaneously soon afterwards. So the instantaneous rate of change for this population. So this allows us to tells us what the change in our population is going to be for each of these different classes, if you like. Okay, so f describes the rate of change for our state variables. I'm missing a little vector notation of that. And typically, when we're writing these systems down, we drop the time dependence t. We just write x, just because the time dependence is already implicit in the fact that we're taking a derivative with respect to time. Yeah.
Could we think of f as like the total rate of change for the state variables, like the vector?
I mean, yes, if you like, it depends on kind of the context. What do you mean like total? I mean, it could be, if you were to sum over these and this was just one population, it would be the total change in the population size if you sum over them. Assuming, well, then, yeah, you would have to actually take the dot product with the population sizes to get these, if it's depending on the scenario, especially if you're dealing with some frequencies. But yeah, you can think of this as just, this is the rate of change for population class 1. So rate of change for, say, your prey, rate of change for your predators, and so on, or rate of change for juveniles, rate of change for adults. So, yeah. Okay. So for linear stability analysis, when we say linear stability analysis, what we're really talking about is what happens in the long term. Okay, so we talk about transient dynamics, and then we talk about long-term dynamics. Really what we're saying is what happens as time t tends towards infinity. So to do this process of linear stability analysis, the first stage of that is finding any equilibria or steady states that we have in our system. We then linearize our system close to our equilibrium. If you recall, I said up here that we're dealing with non-linear systems of ODEs. We linearize that system because it's easier to deal with linear systems than it is to deal with non-linear systems. And then using that linear system, we say, okay, what happens close to that equilibrium? Okay, what happens if there's a small perturbation away from that equilibrium? Does that perturbation tend to grow with time, or does it decay? And this stage here is our linear stability analysis. Really, the linearization step is included in that as well. So first of all, let's talk about equilibria. And in general, we say that an equilibrium, a steady state of our system, we'll call this X star. And we're still using vector notation here. So here, all it means is that F, when it's evaluated at X star, is just equal to 0. In other words, this implies that our dx dt, when evaluated at X equals X star, is just going to equal 0. So there's no rate of change for any of the state variables that we have. What does this mean then? Well, it means that if our initial population, X at time 0, is equal to this X star, all of our state variables are equal to ones given by this X star, then dx dt is just going to equal 0 for all time. So if you start there, you stay there. That's all it really means for it to be an equilibrium. And we stay there forever. That's not super interesting, though. We're pretty unlikely in general to start at an equilibrium. What we really want to know is, suppose this is my equilibrium, what happens if I start a little bit away from it? Am I going to move back towards it, or am I going to move away? I've not indicated what the dimension is here. This could be one-dimensional along a line. This could be two-dimensional in a plane. It could be three-dimensional and so on. Okay. All that really matters is we've moved a little bit away from that equilibrium, and we want to know if we're going to move back to it. So how do we do that then? Well, let's consider that small perturbation. So perturbation is just talking about a little bit of a movement away from our equilibrium here. And throughout this, we're doing local stability analysis. That's why it's only a small perturbation. Okay, we can't say with this what's going to happen if we're very, very far away from our equilibrium. It might be that we would still perhaps tend towards that equilibrium. It might actually be what's called a global attractor. Whatever your initial conditions, you might end up there. That's not always the case, though. Sometimes there's a basin of attraction, which means that you say only tend towards an equilibrium if you start relatively close to it. There might be other equilibria that you tend to if you start close to those. You can think of that as being like two valleys, and there's a ridge between them. And if you start in one of the valleys, you'll tend towards water or ball or whatever will tend towards the center of this valley. If you start on the other side of the ridge, you'll tend towards the other valley. Okay, so just like river basins, there are basins with traction. So all of our analysis here, because we're going to be essentially dropping all of our higher order terms to look at just linear systems rather than nonlinear systems, we can only, that approximation is only valid relatively close to our equilibrium. As soon as we go far away, it no longer applies. Okay. Okay, so let's define something new. Let's define y. Let's define y of t to be equal to x of t minus x star. And so this is just a vector y1 of t, y2 of t, so on, for yn of t. So this y is then our perturbation. It's telling us, okay, if x star is our equilibrium, and we're going to move a little bit away from it, then this y of t, if it keeps growing, then we're not going to be tending back towards x star. If it decays towards zero vector, then we're eventually going to be moving back towards this x star. So what are the dynamics of this? Well, we want to work out what is dy dt. Just differentiate the right-hand side with respect to time. So you end up with dx dt minus dx star dt. Now we know what dx dt is. We've just worked this out. We were told what this is, right? This is our initial system that we have. And this dx star dt, well, this is going to be equal to 0. Right? Because that's just our equilibrium. If you're there, nothing's changing. Yeah.
So x star is really just some constant.
Essentially, yeah, it's just a vector. Right? So really, this boils down to being our vector function f of x of t. But what we can do is we can do a Taylor series approximation of this. So because x star of t is going to equal y of t plus, oh, sorry, x of t is going to be equal to y of t plus x star. We can just substitute this in here. So we have y of t plus x star. And then now we do our Taylor series expansion about x equals x star. This means if we drop all of our higher order terms, so everything that's above linear, we're going to end up with an f of x star plus a load of first order partial derivatives, dfi, dxj, evaluated at x equals x star, times by yi t, and this is summing over all I and j. Here we said this system was n-dimensional. I is 1 to n, j is 1 to n, every possible combination of our partial derivatives of our function f. So this f sub I, if you remember, just go back to this first slide here. These are just these individual components telling you the rate of change for state variable I. When I say state variable, you can just think of this like population class. That's easy to think of, okay? We take all of those partial derivatives with respect to every one of our xj's. So you can think of this then as being an n-dimensional matrix where you have every possible, all of your rows in that matrix will end up being your functions, your rate of change for that particular population class. And then each of the columns is going to be taking the partial derivative with respect to those n different populations. Okay? So this is our Taylor series expansion. About x equal x star. You know, here, this f of x star by definition is going to equal 0. Technically, 0 vector. And so we just end up with this term here with all of our partial derivatives. Remember, if we were doing the exact thing, then we would have had plus all of these higher order terms. And we're assuming we're dropping all of those higher order terms. The reason we can do this as well is because if you think about any nonlinear system, think about like a nonlinear surface, take, say, a sphere. If you zoom in enough on that sphere, everything eventually looks roughly linear, no matter how nonlinear it is. If you zoom in enough, it looks nonlinear. That's why, you know, people think the Earth is flat. Okay, so if you zoom in enough, things look roughly linear. It's a reasonable approximation at a local scale. So this is just a linear system now. Why do we care about linear systems? Well, linear systems are a lot simpler. They basically just grow, stay the same, or decay. Any questions so far? Yeah.
Yeah, so where did our non-linear terms drop out?
So we dropped them out here on this approximation here. So there would ordinarily, if you did the full Taylor series expansion, there'd be an infinite number of terms here
Right.
that we would have, including you know, second order partial derivatives and third order and so on.
Mhm.
However, because we're doing that zooming in and assuming that everything is roughly linear, it basically means that these terms, so we'll have like y squareds and things like that in.
Right.
They are of a much smaller size than y, because we're assuming that this is a small perturbation, so y is very small. Yeah.
Mhm.
Any other questions? Nope. Okay. So we've got a non-linear, we've got a linear system now for our perturbation dynamics. Remember, this is just the perturbation, it's not the full system. But we can now write dy dt is equal to j star y, where j star is the Jacobian matrix evaluated at x equal x star. Otherwise, evaluated at our equilibrium. So that Jacobian matrix is just this matrix that I described with these components on this slide here. Your rows are just your functions, your rates of change f of I for each of the different population classes. And then your columns, you're taking the partial derivative with respect to population class J. So row I, column J. This is your rate of change for population class I, taking the partial derivative with population class J, state variable J. This gives you an n by n matrix, and we call this, excuse me, we call this n by n matrix the Jacobian. So this is nice because this is now a linear system. And we can write down the solution of a linear system, the general solution of a linear system, y of t here is just going to be the sum of n different terms, I equals 1 to n, of some constants, which I'll call ci, times by exponential of lambda I times by t times by vectors vi. Okay, so if you sum together all of these different terms, this is the general solution of this linear system here. So that's why it's nice, because we can write down the solution straight away. What are these different components? Well, I said these CIs are just constants. These constants are determined by our initial conditions. In fact, when we're doing linear stability analysis, we don't actually care about what these constants are. Okay. If you were trying to solve this system, if you had some linear system that you're trying to solve, if you had an initial value problem where you had a set of initial conditions, you find your general solution, and then you plug in those initial conditions to find these constants. But here, if we're doing linear stability analysis, we actually don't care about those constants, because all we care about is this thing stable or not, and maybe something about its stability. Does it like oscillate or not? Okay. These other terms here, the lambda i's, are our eigenvalues of our Jacobian matrix. Can everyone remember how to find eigenvalues? I see some nods. Okay, that's good. If not, you might need a refresher on that. We find out eigenvalues from our characteristic equation. We'll talk a little bit more about that in a moment. And then the VIs are the corresponding eigenvectors. Well, again, from that Jacobian matrix. We have n of these because this is an n by n Jacobian matrix. Okay, so that's the general solution. How does that help us? Well, because these are all exponential terms here, we can see that if the real part of these lambda i's is all negative, all of these lambda i's have negative real part, then we have e to the minus something by t. Yes.
So you said we have n eigenvectors, right?
Yeah.
So aren't we assuming that each of our eigenvalues are distinct then?
We are in this case, yeah. So yeah, this here I should put as a or distinct eigenvalues. Yeah. So this is a special case. Yeah, I didn't want to go into the sort of the detailed case of all the other ones, but yeah, if we have n distinct eigenvalues, then this is the general. Okay, so if of these n eigenvalues that are distinct, if they all have negative real parts, then we're going to have e to the minus something times by t. As t gets very, very large, e to the minus something times by something very large is going to be tending towards 0. So every one of these components will tend towards 0. What does that mean then? Well, that means that our y of t will tend towards 0 as t tends towards infinity. What was our y of t? Our y of t we define up here, the x of t minus x star. In other words, this quantity will tend towards 0 if all of our eigenvalues have negative real parts, as t gets very, very large. In other words, our perturbation will decay away, and if we start close enough to our x star that this linear approximation holds, we'll just tend towards x star. In other words, it's stable. Like I said, the perturbation then either grows. So I haven't covered the growth yet, but the scenario I just covered is only if all of these eigenvalues have negative real parts, it's stable. If any one of these eigenvalues have positive real parts, then we have e to the power of something that is positive, that's by t. So it's going to be tending towards e to something very, very large. So it's going to blow up. It might not blow up in every direction, but it will blow up in at least one direction. That means that there is some way in which we are moving away from that equilibrium. If you think about having your equilibrium as just a sort of a point, and then there's a circle around it in 2D or a sphere around it in 3D, and so on, there'll be at least some area within that sphere or that circle. There'll be some trajectory that takes you away from it. But that's not what we want. We want to be able to say, okay, if you start close enough in any direction, we're going to tend towards that. Okay. So if that's not satisfied, then the system will either grow. If it is satisfied, then if any perturbation will decay away, in which case we have an asymptotically stable system. If our eigenvalues, or at least some of our eigenvalues, have 0 real part, that means that there's in some direction where we are not decaying back towards it, but we're also not moving away as t tends towards infinity. So this kind of gives us this slightly weird scenario there where there's some kind of like constant motion, perhaps. We're not tending towards our equilibrium, we're not moving away from it, okay? So we say that those are stable, they're just not asymptotically stable. So if we summarize that then if the real part of our eigenvalues is negative, all of our eigenvalues for all I, that implies local asymptotic stability, which I just refer to as asymptotic stability. Typically, rather than saying locally asymptotically stable every time, I will just, going forwards, generally refer to things as being stable. Unless I say otherwise, when I say stable, assume I mean locally asymptotically stable, okay? If the real part of any of our eigenvalues, it doesn't have to be all of them. So for at least one I, if eigenvalues if at least one of your eigenvalues has a positive real part, then we're going to be growing away from our perturbation is going to grow away from our equilibrium. That means that it is unstable. These are the cases that we really care about. Note that I've been talking about the real parts. If we do have complex eigenvalues, the stability is just determined by the real parts in the case of, is it stable or unstable? But by Euler's formula, we can also see that if we have some, I'll just do it for the case of one eigenvalue here, lambda, e to the lambda t could be written as e to the a plus bi times by t, if lambda is complex. A and b are just going to be real constants here, and I is imaginary. By Euler's formula, we can write this as e to the at times by cos of b of t, sorry, b times by t, plus I sine b times by t. So if we have some complex eigenvalues, that means there must be some oscillatory dynamics in this system. Ultimately, though, this A here is from the real part of this eigenvalue. And again, we have the same scenario as above, right? If the real part of this eigenvalue is positive, then these oscillations are going to be growing. If the real part of these eigenvalues are negative, those oscillations are going to decay away to zero. In which case, we don't really care about them when we're doing adaptive dynamics. So if you're doing sort of general, linear stability analysis for some population dynamic system, you care about, is it oscillating or not, all these things. For adaptive dynamics, we really just care about this stage here. Is it stable or not? We don't care because we're just assuming the separation of ecological and evolutionary timescales. We're essentially assuming that t tends towards infinity before there is a mutation anyway. So it doesn't matter how you get there, as long as you get there in the end. Okay, so if the real part of these eigenvalues is negative, these decay away, that's fine. And if it's zero, then we end up with this situation where you have some constant motion. Those oscillations are neither growing nor decaying. I mentioned also about this being local stability. Remember, not global stability. This can be a bit of an issue if you have multiple equilibria. If you have multiple equilibria, you don't necessarily know where you're going to. This doesn't tell you about the basins of attraction, right? It doesn't tell you how close you actually need to be. Yes, very good question.
I was just wondering what you mean by constant motion in case that's equal to zero. If I'm having trouble differentiating that from like asymptotically stable.
Sure. Okay. I'm going to jump ahead just to this slide here, just because it's a little bit easier to describe here. So I mentioned oscillations then, for example. One possibility that we can have with oscillations is that they will decay to zero. So in sort of 2D, it will look like this. Like this. So yeah, so you have some perturbation and that decays away to zero. It could alternatively grow like this in case those oscillations are growing away. However, we'll get to what this slide means in a moment. Between these things, we can have something called a center. And here, they're drawn as circles, but they could be ellipses. Basically means that those oscillations are neither growing or decaying, right? And here, in fact, this is referred to as something as being neutrally stable in this case. Those oscillations neither grow nor decay in terms of their sort of overall amplitude. So depending on your initial conditions in this scenario, you just keep going round forever. Okay, so yeah, you can think of that constant motion as being, you can actually write down a constant of motion in those systems depending on how you write down the system. We're not going to go into that in too much detail, so I don't want to sort of digress too much, but essentially just think of them as being, you have stable and unstable, oscillations are shrinking, oscillations are growing, and then between them, there's a knife edge essentially between them where they're neither growing nor decaying. Okay, great. I'll come back to that slide in a minute. Okay, just as an aside, so In the case of a one-dimensional ODE, things are much simpler because we don't have a Jacobian. I just wanted to run through this special case because we'll often be dealing with this special case. So if we have a dy dt now, so we have a dx dt, say, is equal to f of x, where x is one-dimensional, so x is just in R. In this scenario here, again, we do our linearization just as we did before, the same rules apply. We're going to have f of x star plus df dx times by y. This is our, so we've got y is equal to x minus x star. That's our perturbation. And then this here is our Taylor series expansion about x star. So you're exactly the same as what we did before, just in one dimension rather than n dimension. So it's much simpler now. As before, this is going to equal 0 because x star is our equilibrium. So there must be no change there. So we end up with just df dx, that's by y, lambda y. So here we've got dy dt is equal to lambda y. You can solve this. Hopefully you can solve this. This just gives you y of t is equal to y0 e to the lambda t. Where y of 0 is equal to y0. So y0 is just a constant. This is obviously very similar to what we had before, one dimension rather than n dimension, so it's much more straightforward. And so as before, x star is locally asymptotically stable. I'll abbreviate to LAS, if and only if lambda is less than 0. Note we can't have a complex eigenvalue here, so you can't have oscillations. So here, in this case, you only have to look at, if you're just in one dimension, you just have to look at the derivative of your right-hand side of your equation with respect to your population. If we're in two dimensions, because, sorry, yes.
So,
Yeah, no, it's okay, please interrupt, yeah.
I had a quick question.
Of course, yeah.
You switched your variable from x to t. Was that for a reason or curious?
From x to,
Like you have dy dt, but then you have df dx in the same line as the very first line of your dy dt.
here.
Yeah.
It's because, remember when we're doing, if I just go back up to this slide here, we're taking our partial derivatives with respect to our state variable x.
Right.
Yeah? Okay.
Mhm.
So just the same here, we take our partial derivatives with respect to our state variable x, and then we multiply these by the size of our population y. Okay. And again, this is, I haven't included it here. Strictly, this should be evaluated at x equals x star. Okay, I wanted to run through, so I've run through the 1D case, and we'll go through the 2D case as well, just because these are relatively simple, and you'll be meeting these often during the rest of the course. So for a 2x2 matrix A, just as a general 2x2 matrix, but really we'll be thinking about a Jacobian matrix. We want to find our eigenvalues. You don't actually have to find the eigenvalues themselves. All we care about ultimately for adaptive dynamics, remember, is this equilibrium stable, asymptotically stable or not? If it's asymptotically stable, we can substitute that into our evolutionary stage and calculate our innovation fitness. Okay, that's all we care about. So we don't actually care about finding the actual solution vector. We don't care about, are the oscillate, is this a stable spiral? Is it a degenerate case? Is it a stable node? Any of that stuff, we just care as it's. So one of the shortcuts you can take with a general matrix A that's 2x2, if you find its characteristic equation, then this is given by lambda squared minus the trace of A times by lambda plus the determinant of A is equal to 0. Okay, that's the characteristic polynomial for for a 2x2 matrix with eigenvalues lambda. Hence, if the trace is negative and the determinant is positive, then our eigenvalues are guaranteed to have negative real part. Okay, so when it comes to analyzing these systems, you don't have to find all the eigenvalues. You could just look at your Jacobian if we go all the way back up to here. If this was a 2x2 system, you don't have to find this solution here. You don't even have to find the eigenvalues. All you need to do is work out the trace and determinant of this if it's a 2x2 matrix, and then you can use these conditions known as the Routh-Hurwitz conditions to say, therefore, it is locally asymptotically stable, our equilibrium, because our eigenvalues all have negative real part. Nice and simple, okay? If, just as a sort of for completion here, note that if your trace squared minus 4 times the determinant is negative, this is your discriminant here, this quadratic. If that's negative, then our eigenvalues are going to be complex. And that means we're going to have oscillatory dynamics. Again, this doesn't really matter for adaptive dynamics because all we care about is essentially this stage here. I'm just including this here as a reminder. This will give you oscillatory dynamics in your ecological system. Okay. So ultimately, I showed this sort of phase portrait here, showing all the different possible outcomes that we can get in a 2x2 system. For adaptive dynamics, what we want is we want to just be in this top left quadrant here. So this diagram is just showing what happens depending on the trace and determinant of your Jacobian. We want to have a negative trace and a positive determinant. This gives you your Routh-Hurwitz conditions. You'll either have a sink there, a node, or a spiral sink, or a degenerate sink. As long as we're in this top left corner, that's all that matters. Okay, we've got a little bit of time left. I know what you guys are going to say, but I'll ask it anyway. Here is an example of a model of interspecific competition. We're not going to talk about evolution at all here. We're just thinking about the population dynamics, the ecology. And we're going to use linear stability analysis to find the equilibria first and then see whether those equilibria are stable. I'm going to guess, that's what you guys are going to say already. Would you like to do this as an exercise or would you like me to work through this with you? Now, hands up, who wants to do this as an exercise? Oh, you've surprised me, a few of you. Who wants me to work through this? Sorry to the first lot you guys have been outvoted. Okay. We haven't got a ton of time left anyway, so maybe it's best we work through it. So hopefully you'll be fully confident how to do these analyses. Okay, so here this is a model of interspecific competition. We recently met a model that we talked about intraspecific competition. Really, these are the same models. Functionally, they are the same models, but depends on how you kind of frame your question. This version of this Locke-Volterra competition model is being framed as two species, U and V. We talked about this model essentially as being within a species with different phenotypes. Functionally, though, they're essentially the same thing. You might not sort of recognize it. You remember before we had something that looked like this, dni dt is equal to r ni, that's by 1 minus sum of aij nj over ki. Hopefully you guys can remember this is what the model we met recently. This is essentially the same model. All that has happened here is that this has been rescaled. So you can think of this as being your N1 and this as being your N2 in some sense. This has been rescaled just to eliminate some of the parameters, make it a little bit easier. Okay. That rescaling though that's why there's scaled population densities. We've scaled time as well, just so that it simplifies things a little bit. Okay. The key parameters here though are these A's and B's. And this A and this B essentially come from your AIJs in this competition model. Okay. It's just a rescaling. It's not super important at the moment what that rescaling is. I just wanted to let you know that this is not a completely alien model. It's essentially the same thing. We also have this other parameter here, S, and S is the relative rate of intrinsic growth for species 2 compared to species 1. That doesn't actually matter. Yeah.
You said you scaled time. What did you mean by that?
Good question. So whenever we have like a system of ODEs, we can generally, like in a sort of biological context, we can generally scale by two things, usually. We can normally rescale the population sizes. So for example, typically we'll divide by something like the carrying capacity, and therefore our U's and V's now are essentially in terms of the like a proportion of the total carrying capacity. So we've rescaled the population sizes. It's still the same model. We've just essentially multiplied all of our variables by a number. We can do a similar thing with time, that we can sort of rescale time according to some parameters in our model. So for example, in like an infectious disease model, we might have initially our time might be measured in days, say, and all of our rates are in terms of days, but maybe we want to rescale this in terms of the average duration of an infection. So that means that we can maybe eliminate one of our parameters from our system, and now 1 unit of time in that model is actually just, say the average duration of infection was 7 days. It's just stretched time in some sense. We do this because it allows us often to simplify the model a little, but it's still the same model in terms of it will still have the same stability and all of that. Everything's just been sort of stretched in a time dimension as well as being stretched in terms of a population size. Does that make sense? If you want to learn more about that, come along to Math 360 in the fall. Shameless plug. In Math 360, we do a lot of population dynamics. So I hope to see you guys, some of you guys there. Mark will give it rave reviews, right, Mark? There we go. Okay. Right, let's go through this model here. So first of all, equilibria. So we want to solve this model here when both of these equations are equal to 0. Okay, simultaneously equal to 0 means that there's no change in either of these population sizes. We must be at an equilibrium for the system. Okay. So arbitrarily, I'm going to say, okay, what happens when du dt is equal to 0? What I'll do is I'll try and keep the equations on the slide as well for a little bit. So if du dt is equal to 0, that means that either u must equal 0, we call it u star. So this term must equal 0, or the thing in the brackets, 1 minus u star minus ab star must equal 0. Or in other words, u star must equal 1 minus ab star. So for that first equation to equal 0, either u star must equal 0 or u star must equal 1 minus ab star. And then what I'm going to do is I'm going to take in turns, first of all, this first case here, substitute this into the second equation when it's equal to 0. Okay, so if u star is equal to 0 and dv dt is equal to 0, that means that either, just go back up to this equation here, get rid of these things. Again, for dv dt to be equal to 0, we either need b star to be equal to 0. Remember, the stars are just referring to the fact that it's an equilibrium. Or the term in the brackets, 1 minus bu star minus v star must equal 0. We've already assumed that u star is equal to 0 here. This means that v star must equal 1. So that means that we've got two equilibria already. One with u star is equal to 0 and v star is equal to 0. The other with u star is equal to 0 and v star is equal to 1. And then all we do now, that's case 1, if you like, this first case here. Now I look at this second case here. What if u star is equal to 1 minus ab star? And again, I substitute that into the second equation. So if u star is equal to 1 minus ab star, and again, dv dt is equal to 0, that means that, again, it's possible that v star is equal to 0, because this is just the term on the outside of the brackets. If v star is equal to 0, dv dt is automatically equal to 0. And if v star is equal to 0 in this case, u star is equal to 1 minus ab star. So u star is equal to 1. So again, we've got another equilibrium here. V star is 0 and u star is 1. Or if B star is not equal to 0, we have the term in the brackets, which was 1 minus B U star. U star is equal to 1 minus AB star, so I can just substitute this straight in here. B star minus B star. And this is equal to 0. So all I've done here is I've said, okay, we've got U star is equal to 1 minus AB star. B star is non-zero. Therefore, this term here must equal 0. Substituted it in. You rearrange this and you end up with V star is 1 minus B over 1 minus AB. And this is true for B less than 1 and AB less than 1, or B greater than 1 and AB greater than 1. Reason being that we can't divide by 0, so AB can't equal 1. And also, because we're talking about biological populations here, it can't be equal to 0 and it can't be negative. It can't be equal to 0 because I've already assumed that B star is non-zero. So this gives me a value here for B star. I now just need to substitute it back into my equation up here for U star. If you do that, you end up with U star is equal to 1 minus A over 1 minus AB. Again, for A less than 1 and AB less than 1, or A greater than 1 and AB greater than 1. Turns out, in fact, that this coexistence equilibrium, so we've got 4 equilibria now. I won't write them all out again, but I've underlined them, I've color-coded them. The one in red, this is the one we're actually going to explore in more detail here. U star B star is equal to 1 minus A, 1 minus AB, and 1 minus B over 1 minus AB. So we get coexistence in this case if either AB is less than 1 or AB is greater than 1. I appreciate I'm going through this a little bit quickly, just because we're running out of time and I want to make sure we get through to the linear stability analysis on the next slide. All of this will be on the notes online though. Okay, so let's do the linear stability analysis because this is the bit that we really care about for this lecture. So the first thing we need to do is we need to calculate our Jacobian matrix. And we're evaluating it in this case, you would normally go through all of your different equilibria and evaluate all of those equilibria and work out the stability for each of them independently. I'm just going to do this for our coexistence equilibrium. With our general Jacobian, remember what we're doing is we're taking our partial, so as J is going to be df du, and we'll have df duv, dg, du, dg, dv. So we're taking all possible partial derivatives. This matrix of these two variables. If you work that out, you end up here with 1 minus 2u star minus ab star minus au star minus bu star s times by 1 minus bu star minus 2b star. Again, apologies for going through that a little bit quickly. I'm not showing you how I'd work those out. Those are just the partial derivatives from before. What I would encourage you to do after this lecture, if you're not 100% sure on this, is work through this yourself in your own time, your own pace, and check that you end up with the same answers as me. Hopefully I've not made any mistakes. Okay. This would be good practice if you're not familiar with linear stability analysis. At our coexistence equilibrium, so we just substitute in what I've got in red here into that matrix, and then I want to find the eigenvalues. Now tell me, is this coexistence equilibrium stable or unstable? Turns out if you do that, you end up with minus u star minus au star minus bsv star minus sv star. I've actually not fully substituted them in here just for brevity, but this is what you should end up with. You can actually leave things in terms of the U stars and V stars here. And remember, because we're talking about this coexistence equilibrium, we're assuming that U star and V star are non-zero by definition. Okay, so this is a 2x2 matrix. We can use the Routh-Hurwitz criteria to find out whether this equilibrium is going to be stable or not. So does this matrix here have eigenvalues of negative real parts? We just need to look at the trace. So the trace of our Jacobian now, it's going to be minus U star minus SV star. U star and V star are positive, as is S. So this is going to be negative. The other condition we have from our Routh-Hurwitz conditions is to look at the determinant. Determinant's a little bit more complicated here, but not too bad. I'm going to have SU star V star minus AB S U star V star, which is just SU star V star times by 1 minus AB. Now, if I just quickly jump back up to this slide here, our eigenvalues have negative real parts if and only if the trace is negative, which we've already shown, and the determinant is positive. So we need this determinant down here to be positive. SU star and V star are all positive. So this is greater than 0 if AB is less than 1. You can also then go on if you wanted to look at the trace squared minus 4 times the determinant. Is this going to be oscillatory or not? But actually, as far as if you were doing adaptive dynamics, this would be the stage that you'd need to stop at. You found a condition for when this coexistence equilibrium is locally asymptotically stable, as long as AB is less than 1. We tend towards this equilibrium in the long term. Okay. I have office hours now in case anyone has follow-up questions. If not, I will see you guys on Wednesday, where we will be talking about something called convergent stability for adaptive dynamics. Okay, thanks everyone.